So in this video I'd like to talk about the power of the point. So the power of a point is a set of theorems that are really useful for calculating various pieces of length. So it begins with a circle and a point either outside the circle like in case 1 or inside the circle like in case 2. And then two lines passing through that point and bumping into the circle. So we've got AB on the same line and CD on the same line, same thing in this picture. What the power of the point says that in this scenario, the length PA times the length PB is equal to PC times PD. So even though the two pictures look different, the statement is the same and the proof is actually the same thing. So to prove this theorem, what we'll do is we'll begin by connecting AD and BC in both pictures. Now we see over in this picture that angle PBC and PDA are the same because they're both coming off the arc AC, so that's by Thales' theorem. The same thing is happening over here. PBC and PDA are both coming off of arc AC, so they're also the same. Next, we see that angle BPC is equal to angle DPA. That's because they're the same angle. Over here it's slightly different, but we see that BPC is equal to DPA simply because they're opposite angles. Now we conclude that by similar triangles, triangle BPC is similar to triangle DPA. And so now we can conclude that PB over PD is equal to PC over PA. And finally, if we cross-multiply this statement, what we end up with is exactly the result. We end up with PA times PB is equal to PC times PD. The theorem still holds if one of the lines are actually tangent. So this line PT isn't crossing through the circle, but it is touching the circle. And what we end up with is we end up with PA, PB is equal to PT squared. Now to prove this, we'll have to introduce the center of the circle. So it doesn't matter if the line AB is below the center or above, it will work out in the same way. But what I'll do here is I'll just put a center in, and I'll add a line that passes through P in the center of the circle. Now I'll label where this line enters and leaves the circle as C and D. Now we know that by the original case that PA, PB equals PC, PD. But we also know that for tangent lines, if we are to connect the center of the circle down to T, that it creates a 90 degrees. So what I'm going to do is I'm going to manipulate the PC and PD part so that I can use this 90 degrees. So I'll replace PC with PO, so I'll call this center here O. I'll replace PC with PO minus the radius. And PD I can write as PO plus a radius. Now, when I multiply these two together, I get a difference of squares. But what we recognize here is that PO squared is the hypotenuse of the triangle POT. So PO squared minus R squared ends up giving me exactly PT squared. If we put bars on the product PA, PB, so that they're now directed distances, then this product tells us even more about the relationship between P and the circle. In particular, we see that if PA times PB is positive, then both PA and PB must go in the same direction. So we would have something like PAB. So both PA and PB are moving to the right. So they would either be positive times positive or negative times negative, but in either case we'd get a positive answer. If PA times PB is equal to 0, though, that means that one of PA or PB has to be 0. Well, the only way that a statement PA, for example, could be 0 is if P and A were the same point. So PA, PB equals 0 means that either P is on the circle and it's point A, or P is on the circle and it's point B. And then for P inside the circle, that's when PA and PB are in different directions. So if we just draw this, if we put P somewhere in here and call this A and B, then we see that PA is going in one direction while PB is going in the other. So their product is going to be a negative product. So it's actually this product with the bars over it that we call the power of P with respect to the circle. Here we have a cute application of the power of the point. So suppose that there's a lily pad growing in a pond, and when you lift the lily pad up so that the stalk is pulled tightly, there are 10 centimeters of stalk that are showing out of the water. Then when you let the lily pad go, it floats 50 centimeters away from where its stalk met the water when you were pulling on it. And the question is, how deep is the pond? So I'm going to just draw a little picture here. So suppose that this is the surface of the water, and we'll have the lily pad here, and somewhere down here it's anchored into the water. So we've got our lily pad up here. Okay, I'm not a great drawer, you'll have to forgive me. So here we're assuming that this poking out of it is 10 centimeters. We want to find this depth here, which I'll call x. Well, if I imagine this point where the lily pad attaches to the bottom of the pond as the center of a circle, so I'll just put down here, this is the surface, the bottom of the pond. Well, this ray here can be used as a radius to make a circle. So I would end up with a circle that looked kind of like this. And I'll only draw half of the circle for now so that we can get started on the rest of the picture. But what we're told is that if we let go of the lily pad, it will float, and it will float away, and it will go in this direction here, and the distance here, we're told, will be 50 centimeters. So we have 10 centimeters there and 50 centimeters here. And then we see, well, if the wind changed, it would float the other direction, and so this should also be 50 centimeters. So now what we want to do is I just want to extend my circle so that we see the whole picture. I'm just going to shrink the image here so that I can do this. So if I draw the whole circle, then down here, this part would just be the radius. So what I want to do is I want to use the power of the point to actually calculate what this x is, because that would be the depth of the pond. So I'm going to place here, where these two lines meet, where we have some kind of numerical data information, that's what I'm going to call P. And so now we have, so I'll just label some other points. I'll call this A and B, and where this ray comes out of the circle, I'll call this C, and then way down here where it comes out of the circle, I'll just call that D. And so by the power of the point, we know that PA times PB equals PC times PD. Well, we know that PA and PB are both 50, so this gives me 50 squared is equal to PC, we also know it as 10, and PD is this remaining part here. So if we want to talk about PD, we could just leave it as PD, but let's actually break it down so that we have it in x's. So PD would be x plus a full radius again, and we see that the radius is x plus 10. So PD is x plus 10. So this, when we tidy it up, gives us 2,500 equals 10 times 2x plus 10. So now we just want to solve for our x. So we have 250 and I'll minus this 10 away from it, is equal to 2x. So this gives me 240, and then I'll divide that by the 2. So this gives me 240 divided by 2 is 120, is equal to x. So now we can say, so therefore, the pond is 120 centimeters deep. So our last example was a cute example, but kind of silly. Here, though, we have something where we can really see the practicality of using the theorem, the power of the point. So I'd like to calculate the diameter of the Earth using some very basic calculations and some geometry. So suppose that Mount Zeus in Naxos is approximately 1 kilometer at its highest point. Looking from Mount Zeus, a viewer can see Milos, another island, which is about 113 kilometers away on the edge of the horizon. I want to use this information alone together with the power of the point to approximate the diameter of the Earth. So what I'm going to do is I'm just going to draw an image here. So we're going to pretend that our circle here is the Earth, and then I'm going to have, this is my little mountain, and I'm going to assume, now this is not drawn to scale, I'm going to assume that this distance is 1 kilometer above the rest of the Earth. And so then what I want to do is I actually want to take this point here, and I want to extend it. Now, a view on the horizon, when we look out to the horizon from a tall structure, it means our eyes are making a tangent line to the horizon, or a tangent line to the Earth. So I draw my tangent line like this, and so this is going to be my T point, and this is going to be my P point. So I need to extend this down, and so that means that I would call this thing here A, and this thing here B. So, sorry, that doesn't look like a P. Alright, so now what I know is I know that Milos is 113 kilometers away from the mountain. And so I'm going to write that this part here, PT, is 113. And so now what I have is I have that PT squared is equal to PA times PB. Well, PT squared is just 113 squared. PA is this 1 kilometer right here, and then PB, we want to be a little bit careful here. PB is not quite the diameter of the Earth. Our PB is the diameter of the Earth, which we're interested in, so I'll call that D for diameter. And then it's also this plus 1, so PD is the 1 plus D. So I'll write this as 1 plus D. And now we want to solve for D. Okay, so I had to do a little side calculation over here so that I could actually figure out what 13 squared was. But over here I have 12769 is equal to, so this 1 product isn't doing anything, so it's equal to 1 plus D. So I'm just going to subtract 1 from both sides, and I get therefore that 12768 is equal to D. So therefore the diameter of the Earth is approximately 12,768 kilometers.